Hey there, chemistry team. It's a bright new, scorching hot day. Ready for video number 11 for our thermodynamic journey, which is almost at an end. Our canoe is coming up to the side of the dock now. We're about to get off of the canoe onto the dock, but sometimes that's the hardest part, and a lot of people go dump right as they're stepping out. So a lot of people with thermodynamics think this last part is the hardest, calculating the temperature dependency of equilibrium constants. I wouldn't say it's hard, it's just tedious. Multi-step calculations and mathematics and tracking uncertainty is like, oh my God, lots of points though on the test. So I'm going to show you two different ways to do this, but it is, I agree, quite involved to do. We've looked at this qualitatively back in our Le Chatelier's video back in our equilibrium chapter. But in this one, we're going to look at it quantitatively, right? So let me review real quick qualitatively what happens when you increase the temperature. We didn't look at it for the equilibrium constant specifically, but I'll connect the two. Now remember, exothermic versus endothermic. Exothermic reactions, the system is losing heat or releasing heat to the surroundings. And so that would be a negative delta H if you look at it, right? So this would have a negative delta H. Endothermic would have a positive delta H. Because endothermic, it's gaining energy via heat from the surroundings, so it's got a positive delta H. Exothermic, it's losing energy via heat to the surroundings, so it's negative delta H. But remember, we looked at heat as a product or reactant to look at Le Chatelier's principle. So for an exothermic reaction, releasing heat, we treated heat as a product. For endothermic reactions, absorbing heat, we treated heat as a reactant, oversimplifying it, right? So if we increase the temperature on an exothermic reaction, we're increasing the product heat on the right, so it would shift back to the left away from it to counteract it. And that would, in this effect, go more reactants. That would drop your K value, right? Because K is product over reactants. So K would get smaller qualitatively for exothermic reactions. For endothermic, if you increase the temperature, you increase the reactant, so it shifts towards products to compensate, so you create more products, K will go up. All right? So we can kind of predict our answer ahead of time, but review Le Chatelier's principle if you need to. There's two ways we're going to do these problems, and two types of problems. Most commonly, we're going to say, what's the equilibrium constant for some reaction at some temperature? Now, we've only been doing 25 degrees Celsius or 298.15 Kelvin, because when you do that, you can use your thermodynamic tables, right, to calculate your delta G's, but that only works for 25 degrees Celsius. What if we're not at 25 degrees Celsius? Oh no, it complicates the issue, right? So I'm going to show you one way to approach this problem using concepts you already know. It's just lots of steps and very tedious. And then I'm going to show you another way to do it, which kind of combines everything together. Not necessary to do, but it's just like a little trick. It's up to you. I don't care which method you use. So if we calculate K values at any temperature, or vice versa, say, hey, I want this specific equilibrium constant. What temperature would I need to get that? You can do the same thing, it's just backwards. We've got two options. I could care less which one you use. Let's look at those two options on the next board. Okay, gang, here's your two options if we're going to quantitatively look at the impact of temperature changes on equilibrium constants. My preference is the first method, but if you want to do the second method, that's fine. I don't care. I'll give you the equations for everything you need. Step one is using pretty much everything we already know, just a little more advanced because we're not at the temperature where we could use our thermodynamic tables to calculate delta G, right? Any temperature other than 25 degrees Celsius, you can't use that for delta G. Huge capital H mistakes students make on exams. So check your temperature, right? Am I at 25 degrees Celsius or 298.15 Kelvin? If not, it gets more complicated. Here we go. Option number one. We're going to use the two big kahuna equations from thermodynamics. Delta G naught is delta H naught minus T delta S naught. And that we derive from the second law of thermodynamics, right? And then delta G naught is negative RT log K. And that's where the equilibrium constant is. You have to use that one. We're solving for K. It's the only equilibrium, it's the only thermal equation that has K in it, other than the Van Hoff equation, which I'll derive from those two equations in a little bit. All right, step one. Let's calculate delta H naught, the enthalpy change of standard conditions. And we are going to make an assumption, even though we're not at 25 degrees Celsius, we can use our thermodynamic tables to calculate delta H and delta S at any temperature. Right? So step two, we're going to calculate delta S naught, the entropy changes using those tables. We are making an assumption for steps 1 and 2 that both delta H and delta S are temperature independent. Good enough for this level. All right? It makes our lives less miserable. Not necessarily true, though. We know that entropy, the absolute entropy S, is very highly dependent on temperature. Okay, you increase the temperature, you increase the energies and the available number of energy states that they can access, so the number of microstates increases. Think Boltzmann equation. But if you take the difference between them, yeah, theoretically, those should kind of cancel out when you subtract the initial state from the final state. We're going to make that assumption and say that those are temperature dependent. Yay! We can use the tables. Once we have delta H and delta S, and we know the temperature of interest, say it's 127 degrees Celsius, negative 15 Kelvin. We can't have negative 15 Kelvin. That would be lower than zero. That's impossible. So negative 15 degrees Celsius, whatever it is, plug it into this equation and calculate delta G at standard conditions at that temperature, right? If you were at 25 degrees Celsius, you could skip steps 1 and 2 and just go straight to the tables, all right? But we're not at 25 degrees Celsius in this case. So use this equation. You know delta H, step 1. You know delta S, step 2. You know the temperature of interest. Boom, calculate delta G, standard conditions for that particular temperature. Then step 4, we're going to use this equation here. Now that we know delta G, we know R, we know the temperature, we can solve for the equilibrium constant. Boom! The second method would be to use what's called the Van Hoff equation, which I'm going to derive for you in a separate video. So this video will be method 1, the next video will be method 2. But we're just going to take those two equations and merge them together and get it's kind of a cool, algebraic gymnastics process. And we'll go through and do it, but method 1 seems to be more sensical for most students. All right, let's do an actual problem. All right, here's a problem for you, gang. Seems like a simple problem, but it won't be. All right, what is the equilibrium constant at 85.0 degrees Celsius? And the first thing you do on the test, you go, no, it's not at 25 degrees Celsius, so I cannot calculate my delta G using this table. Biggest error students make on their final exam in this class is they just go ahead and calculate delta G using the tables, thinking it's okay to do it at that temperature. It's not. Delta G is way too temperature sensitive, okay? And so when they do that, they literally miss half the problem. -10, they're like, crunch. All right, so note the temperature. That's a critical thing. What am I at that reference temperature, 25 degrees Celsius, so I can use those tables for delta H and delta S, or am I not? In delta G, we can do delta H, delta S for any temperature because we're assuming temperature independency, but you can only use 25 degrees Celsius for delta G for that. Any other temperature, you're like, crud monkeys. So we're at 85.0 degrees Celsius for the following reaction. Doesn't matter what reaction it is. We've got some Fe2O3 solid reacting with 6 moles of HCl gas, not AQ. The state matters, right? Big difference in the values. Giving us 2 moles of FeCl3 solid, so we got some iron 3 chloride solid, and 3 moles of water vapor. That's a gas, not a liquid. Huge error number 2 students make. They use the liquid value on the tables instead of the gas value. All right, step 1, calculate delta H, assuming temperature independency, so we can use this to calculate delta H at any temperature. Yay, good enough for this class. So here's our equation, just like you've seen many times before. It's the same one for delta S, same one for delta G. Take the sum of all your products, stoichiometric coefficient, times the molar enthalpy of formation at standard conditions, which is on the thermodynamic table. Do the same thing and sum it up for your reactants. So our products are the iron 3 chloride solid and the water vapor. So let's take 2, right? We got a 2 in front of the iron 3 chloride, 2 times its value. So we need to look that value up. Let's look up iron on our table. All right, so here's our iron section, right? That was barium. Here's iron. We're looking for iron 3 chloride, which is right there. Iron 3 chloride. Now, delta H is the first column. All right, don't get the wrong column. Iron 3 chloride, is that a negative 399.5? You see that? That's why I put a negative 399.5 kilojoules per molar on the top of the table. Let's add to that, because we're summing, the 3. We got a 3 in front of the water, right? 3 for water gas. So let's look under hydrogen here. Here's hydrogen. Let's look for water. Where's our water, water? So we got water in the gas phase and the liquid phase. We're in the gas phase, as much as Aquaman would like it in the liquid phase. We're in water gas. That's hydrogen peroxide. Water gas is here, negative 241.8. Negative 241.8 kilojoules per mole. That's the summation of our products. Let's do the summation of our reactants. So we've got 1 mole of the Fe2O3. So we put a 1 here. Let's look up the value for Fe2O3. So we'll look under iron again. Ooh, like Iron Man. Fe2O3 is here. That would be negative 824.2 kilojoules per mole. Right there. And then we've got 6 moles. So there's the 6 times the HCl gas. Standard molar enthalpy of formation. What are we looking for? HCl gas. Right there under hydrogen. Not aqueous. We want the gas. So that's negative 92.31. Negative 92.31 kilojoules per mole. Probably the longest part of these problems is looking up the stupid values on the table, right? You're like, oh, I can't see, especially when you're in your 50s like me. You're like, oh, God, I can't read anymore. All right, so let's take 2 times negative 399.5 plus 3 times negative 241.8. This is essentially an addition problem because these 2s and 3s and stuff are exact. So we're limited by decimal places. So to 1 decimal place, I get negative 1,524.4 kilojoules per mole. That's the total summation of our products, our final state. Let's do the same thing for our reactants. 1 times negative 824.2 plus 6 times negative 92.31. Limited to 1 decimal place, so we get negative 1,378.060 kilojoules per mole, good to 1 decimal place. That's our final state for our reactants. Let's take the final state products minus the sum for the initial state reactants, limited to 1 decimal place. I get negative 146.340 kilojoules per mole, good to 1 decimal place. Now let's think about what that means. That's exothermic. Delta H is negative. That's an exothermic reaction. So qualitatively, heat would be a product. So as temperature increases, it shifts left. K should drop, right? So as temperature increases, K decreases for exothermic processes. Now we don't have a reference temperature, but if we calculated K at 298.15 Kelvin, the value at 85 degrees Celsius would be lower than the value at 25 degrees Celsius. That's all we know. But let's calculate it at 85. So go ahead and beat me to the punch. You calculate step 2. Do the exact same thing for delta S. And we're going to assume temperature independency so you can use the thermo tables. I'm going to race you. You ready? Get set. Go! All right, did you beat me? I can cheat, though, because I can cast time stop. I'm like an archmage in Dungeons & Dragons casting, whipping out 9th level spells. Boom, boom, time stop, pause. And then I can just do it and come back. It was like instant. All right, here we go. I just left the problem up on the board there. I actually cheated. I just kept the exact same format. It's the exact same calculation, just different numbers and different units. So everywhere I had an H, I put an S for entropy. And here we use the absolute entropy, not the change, because of the third law of thermodynamics. So just take the product summed minus the reactant sum, minus initial. So for the 2 FeCl3, I took 2 times negative 142.3. And again, joules per mole Kelvin. Entropy is a little bit different. So if you look on the entropy, which is the third column, it's joules per mole Kelvin. So if we look up FeCl3, iron 3 chloride, there's iron. Iron 3 chloride all the way over is negative 142.3 joules per mole Kelvin. All right. For water vapor, we have 3 moles of it, so 3 times the value for water vapor. So look up water. The gas, not liquid, there's water, gas right there. Go to the very last column, and I get 188.8. 188.8 joules per mole Kelvin. That's the summation of our products minus the reactant. So I have 1 mole of Fe2O3 solid. So 1 times. Let's look up Fe2O3 solid. So there's iron. Fe2O3 solid is right there. Go to the last column and I see 87.40 joules per mole Kelvin. And then we've got 6 moles. So there's the 6 times the HCl in the gas phase. Let's look up HCl there in the gas phase, not aqueous, gas phase. Go over to the last column. I get 186.9. 186.9. Get used to those tables. You want to move fast on exams with those babies. You don't be like looking around. Where is it, man? All right, let's take 2 times negative 142.3 plus 3 times 188.8. Good to 1 decimal. I get 281.8 joules per mole Kelvin. That's the summation of all my products, my final state. For the initial state, let's take 1 times 87.40 plus 6 times 186.9. Good to 1 decimal. So I get 1,208.8 joules per mole Kelvin. So if I take my final minus my initial state, products minus reactants, 1 decimal, I get negative 927.0 joules per mole Kelvin. That's a very large negative number. Now, does that make sense? I wrote that there in green. I want you to check that just real quick. Take a little second here on an exam or quiz and go, does that make sense? Look at my reaction. I've got Fe2O3, I got a solid, I got 6 moles of gas, giving me a solid and 3 moles of gas. And remember, one of the biggest things that impacts entropy changes is changing the gases, right? So if you increase the moles of gas, the entropy is going to massively go up, increase translational and rotational states. The microstates go up dramatically, but here we're dropping the moles of gas by half. That's a massive decrease in the available microstates, so the entropy change should be going down. That should be a really negative number, right? So that kind of makes sense. We're really dropping the number of microstates, so delta S should be negative. So that's a quick gut check right there. Go ahead and do step 3 for me. We know delta H from step 1. We know delta S from step 2. We know the temperature of interest. You got to convert that to Kelvin. Plug that, delta G is delta H minus T delta S, assuming delta H and delta S are temperature independent. Go ahead and calculate delta G at 85.0 degrees Celsius for me. See what you get. Let's see what you got, and then let's see what that means. All right, what does each step mean? All right, so step 3, we're going to calculate the Gibbs energy change at standard conditions, but it's at 85.0 degrees Celsius. Again, if this was 25 degrees Celsius, it would be a way easier problem. You wouldn't have to do steps 1 and 2. You wouldn't even have to do this for step 3. You could just go straight to the tables and use that same equation, and so this becomes a 2-step problem. So calculating equilibrium constants at 25 degrees Celsius is 2 steps. At any other temperature is 4 really nasty steps. Well, we need our temperature in Kelvin, right? So let's take our 85.0 degrees Celsius, add our conversion factor 273.15, which is exact. So it's an addition. We're limited to the tenths place. So 358.150 Kelvin, good to the tenths place. So we're 1 decimal. Let's plug our values into one of our King Kahuna problems. Delta G reaction is delta H minus T delta S. I think we got that. We derived that from like the second law of thermodynamics or something, some long windy road. We know delta H from step 1. We know delta S from step 2. We know our temperature. Plug it in. Piece of cake, right? So delta H from step 1 was negative 146.3 kilojoules per mole. Subtract our Kelvin temperature. That was 358.150 Kelvin, right up there. Times our delta S, which was from step 2, negative 927.0 joules per mole Kelvin. That darn entropy. Got the wrong units. Delta H is kilojoules per mole. Delta S is joules per mole Kelvin. So we always have to convert joules to kilojoules. Don't ever forget your units, please. I beg you, don't forget your units. So convert joules to kilojoules. Now we can add apples to apples, right on? So if I take the temperature times the delta S converted to kilojoules, I get negative 332.005 kilojoules per mole. Good to 4 sig figs, both in the delta S and the temperature. So let's take delta H minus the T delta S term. I have to do this, and I had to do the multiplications first, so now I can do the subtractions. That's how a chemist does things. You got to do as many steps as there are different types of rules for uncertainty. Take the negative 146.3 kilojoules per mole minus negative 332.005 kilojoules per mole. Good to one decimal place in both scenarios. So I get a Gibbs energy change of standard conditions of 185.665 kilojoules per mole, good to one decimal place. No need to round it, because in this problem I asked for the equilibrium constant. So don't round anything until you get to the equilibrium constant. Total waste of your time. What does this mean? From one of the prior videos, we had these three different situational graphs where we looked at these curves and what delta G meant and how that impacted K values and whether it was reactant favored or product favored. Well, a large delta G value, positive, right? Positive means, non-spontaneous in the forward direction. But a large delta G meant you had a very, very small K value. So you looked at the curve, and the bottom of that well line was way over on the reactant side. So very small K values are very reactant favored or reactant dominant. And that represents itself as a large positive Gibbs free energy change of standard conditions. So if you don't remember that, look at the prior video. I think it was the one right before this. All right, regardless, if you don't care about that or not, let's go to step 4. Go ahead and do it before I do. Cast your time stop. Boom, 9th level spell. Have at it. If somebody casts a 9th level spell, just run. Right, anyway. And if you don't play D&D, you don't know what I'm talking about. Go to step 4. We now know delta G at 85.0 degrees Celsius. Plug it in. Delta G is negative RT log K, baby. Calculate K for me. All right, I know you beat me to it because I didn't do it. All right, here we go. Step 4, calculate the equilibrium constant at whatever temperature they asked you for. And using this King-Kahuna equation, Gibbs free energy change is equal to negative RT log the equilibrium constant. So what I'm going to do, because I know delta G, took forever to get it. I know R is a constant. I'll give that to you on exams. I know the temperature in Kelvin. So I'm going to solve for log of K first, and then I'll just take E to that, and then I'm good to go. So let's punch this out. So log of K, let's see, I'm going to divide both sides by negative RT. That will be negative delta G naught over RT. All right, so everybody's got that equation there. This could be, because we got to do some conversions, I'm going to move this down to the next line here. So log of K, what was delta G again? Was it one, it was positive, right? 185.6 something. So, but we got the negative sign there, so don't forget that negative sign. 185.6, was it 65 kilojoules per mole? It was good to that one decimal place, right? And a lot of people forget that negative sign. You're toast, right? Got to bring that negative sign down. Now, if delta G was negative, those would cancel out and make it positive. Huge difference! Let's divide by R. And again, in a unit line equation, you're just multiplying by the inverse. So 8.3145 joules per mole Kelvin. You may or may not have that memorized by now. Not necessary to memorize it. I'll give it to you on exams, but I believe in memorization by doing something over and over and over and over. Right? You just use it so many times, you're like, yeah, there I go. Oh, I got to convert to Kelvin at 273.15, yada, yada, yada. And so it just sticks in your brain. Right? But I'll always give it to you because I know sometimes we get brain farts on exams. Oh, I can't remember. Yeah, it's like my kids' birthdays or something. Where it's like, oh crap, well, I know it. Where is it? Having random access memory issues. All right. See the kilojoules there and the joules there? Those don't mix well. So let's convert our joules to kilojoules. You see that happening a lot, right? When you're dealing with these things. So moles cancels out. Kilojoules cancels out. Joules cancels out. And we're taking the log of this, so this has to be unitless. So can you see why we need to divide by the temperature? We got to get rid of the Kelvin, right? So let's divide by our temperature, which you can just go 1 over. That's how you do that in a unit line equation. What was our temperature again? 358.15, something like that. I don't think I have a lot of room here. Oh, major squish. All right. So you have to zoom in on that one there. So I divided by 358.15 Kelvin, good to the 10th place. And Kelvin cancels out now. Boom, boom. That leaves us a unitless quantity, which is what we need when we take the log of something. Good. So log of K, 4 sig figs there. A lot more than that there. That's exact 4 sig figs. So we're good to 4 significant digits. I get negative 62.34, vertical dashed line, 89. So that's the log of K. Now I just take e to both sides. So e to the natural log cancels out and gives us K. E to the negative 62.3489. Let's do it. So K will be e to the negative 62.3489. And remember, when you take e to the power of x or 10 to the power of x, it's opposite logarithms. So logarithms, the number of sig figs becomes the number of decimal places. So for exponential stuff, the number of decimal places becomes the number of significant digits. We have 2 decimal places in that value. The negative 62.3489 is good at 2 decimal places after we do the 4 sig figs, right? So that means we'll get 2 sig figs in our answer. The 2 decimals goes to 2 sig figs. Oh! If you freak out on a test, just guess. Right, here we go. So I get 8.3. There's my 2 sig figs. 60 times 10 to the minus 28th has no units, right? Does that make sense for our prediction from step 3? We had a large positive delta G naught, which means we should have a very, very small K value. That's really small. Very reactant. I mean, pretty much almost all reactants at equilibrium. So we would almost say that that doesn't even go. Now this is the final thing I asked for, so I can round this. So that rounds up to 8.4 times 10 to the minus 28th. And that is at 85.0 degrees Celsius. That's the equilibrium constant at that temperature. I think those are the longest, toughest problems to do in the thermodynamics at this point, right? But if you know your 4 steps, just know your steps. Each step's not so bad. You could do it. Next video, we'll look at what they call the shortcut, the Van Hoff equation to this. We could redo this and get the exact same answer. I don't consider it a shortcut myself, but it's got some cool derivations to it. So we'll do another video after this.